So after our introductory lecture on machine learning, what we're going to dive into a little bit more today is autoencoders. And we already covered PCA many times, many different ways, with many different people. So we're going to motivate our discussion on autoencoders with principal components analysis. And autoencoders are a type of neural network. So, if you really want to argue about it, there's two neural networks, although you can train them as one. And we're going to actually be running that today, so you guys will build your own autoencoder very soon. Okay, so we're going to be talking about autoencoders. All right, so we're going to go through the different architectures in the context of representations, and we're going to motivate it with a lot of the work that we've already done in PCA, and I'm actually going to give you guys a hint of what you should expect in the code later today, and you're going to see how an autoencoder is going to build a representation and a reconstruction. And I know you don't know everything I just said yet, but you will in a few minutes. Okay, so to start off, we all did principal components analysis. You guys are very familiar with it by now. The idea is that you have some input data. For us, it was 150 neurons by 18,000 or so in time. And what we were essentially doing was encoding this data into some representation space. And in this case, it was a lower dimension than we originally had. And so we can then use that representation for a downstream task. To be more concrete, and this is the code that we went through on Monday, you have some number of neurons across time, and that's your input data. You're using an encoder. In this case, we're using principal components analysis, and we're creating some representation. In this case, a three-dimensional space. And then the downstream task, there were many that we explored, but one of them is being able to determine the sex of the intruding animal. And so there's male or female, and we can classify that if that's what we wanted to do with our downstream task. So an autoencoder is basically if you take the first piece of PCA, so you take this piece that's input data to an encoder to a representation, but the way that you want to learn a representation is that it's actually not just a one-step like PCA is, but it's going to be learned instead of just, a compression using dimensions that explain the most variance. And so with an autoencoder, what we're going to do is we're actually going to flip the encoder, and it doesn't necessarily have to be the same size, so it doesn't have to be the same number of layers, it doesn't have to be the same size of layers, but the concept is that you can just take an encoder and flip it, and that's called a decoder. And then what you're going to create is this idea and this, let's say it's called an array, which is a reconstruction. And the reconstruction is supposed to be a reconstruction of your input data. So it's going to be the same dimension, the same representation, the columns and rows mean the exact same thing. And the way that you train your encoder and your decoder is by seeing how well your input data matches the reconstruction. So this would be an example of self-supervised learning. Some people would argue that it's unsupervised learning, but this concept of an autoencoder is very important because what you can then do is you can use this representation that is trained on your ability to do reconstruction to do downstream tasks, whether that be classification or clustering or anything you like. Yeah.
So imagine I have noise in the data,
Mm-hmm.
and then I do reconstruction, and I actually want it to be different than the input data. I want it without the noise.
Right.
So how do I?
Yeah. So this is a good question, and you actually can do that. One of the ways that people train this is what they'll do is they'll take. So we're going to go into like training sets and test sets in a little bit. What you can do is if you take, let's say you have, 100 clean examples and you have 1,000 unclean examples and you have some noise. So the case I'm most familiar with is if you have like a time series neural data, oftentimes with humans, you'll get like an ECG signal on top, and that's noise and you'd like to not have it in your data. So what you can do is you can train an autoencoder to take in clean data that you've corrupted with noise and basically try to get it to reconstruct what just the clean data is. So I'm presenting the simple case where we would like to reconstruct just the input data, but you can have it reconstruct a clean version. Yeah.
What do you compare it to?
Right. So in the way that I'm describing it, what you would need is you would need a few clean examples, and then you would actually add in your own noise. So in this case, you do know what the ground truth is, and then you would compare it to ground truth. And then what you could do is you could take the data that is corrupted pass it through and see what happens. And so people do this. It's part of this larger field called source separation. So the idea is like there are many sources that contribute to the data I'm recording. Some could be like movement, some could be stimulation artifact, some is like the actual signal. And you can learn how do I reconstruct like ECG noise versus stimulation noise versus the actual data. So that is something you can do with autoencoders. We're going to do the most simple case of autoencoders today, which is just, can we learn how to reconstruct the clean input data? But if you're interested, I can send you papers on how you do it with noisy data and how you can use it to get rid of noise in your data. Cool. Any other questions? And that was a very good question. No? Okay. So, I don't know if I said it, but I alluded to it. An encoder is a neural network and a decoder is a neural network. In what we're going to explore today, and with a lot of encoders, this is the case. And just to reiterate, I know I've drawn them to be the same size and the same shape, and today we are going to implement them to be the same depth, meaning number of layers, which we'll get into in a little bit, and the same number of artificial neurons per each of the layers, but they don't have to be. You can have a very simple decoder and like a very complicated encoder, or vice versa, or they can be the same. There's really no constraint to say that the encoder or decoder is different. And oftentimes people will explore, can I get a good embedding where the decoding can be a very simple step and you can do it quickly. So there's, tons of combinations on how you can do this. Okay, so what I'm going to show you now is Mnist, and if you're not familiar with like machine learning at all, Mnist is basically a data set where they take handwritten digits, and what they want to do is they have these handwritten digits, and it's like 28 pixels by 28 pixels, and they want to, it's basically a dummy data set where it's very easy to train on nowadays, and you can basically see how different models perform on it, and you benchmark against it. And so what we're going to look at is what an autoencoder outputs for Mnist, because the representation that Mnist creates is one of the nicer representations that you are ever going to see. So we may not get as nice in fact, we won't get as nice a representation with the neural data that you guys are going to work with today, but this will give you an intuition behind, in the best of all cases, in the most interpretable of all cases, what will we see? And so to give you a little bit more background on Mnist, it is literally handwritten digits. So the top shows you some of the zeros and then the next ones all the way down to nines. And you can see that there's a lot of variability in these digits. There's a different like tilt to the way digits are drawn. There's more curvy sixes, there's more curvy nines, there's more straight ones. And so what our goal to look at now is to really use an autoencoder on Mnist to generate these handwritten digits. So we're going to pass in one of these images. So let's say the bottom left 9. We're going to pass that into a model. We're going to create some latent representation of it. And then we want to reconstruct literally that handwritten digit. Okay, so let me pause here. I'm actually going to let me go back a few slides. So the goal is input data will be that image. We create some representation with it. And then the green, which is the reconstruction, will literally be the image that we created. Does this make sense to everyone?
You're not giving them any labels here, right?
We are not giving them any labels here, yes. So autoencoders are, I would call them self-supervised learning. Other people would call them unsupervised learning. It depends on the context in which you do it, but there are no labels. So in Mnist, if you wanted labels, obviously there are very easy labels like zeros, ones, nines. We're not using the labels. We are only using the image, and we're just trying to reconstruct the image. Yeah, Laura. Here, speak up a little bit.
My question is, what is the function of this? What is the end goal?
Yeah.
Because it seems like you're getting back what you already had. So.
Yeah, and so there are a few things. So oftentimes there are data sets where you will not have a clean label, and there is not a clean way to create like a lower dimensional, if you want it to be lower dimensional representation. And you would like to be able to use that lower dimensional representation to either do downstream tasks, or you just want to see if it's like interpretable and can actually teach you different scientific principles about the data. Or like in Amit's case, which is a really good one, let's say you want to do denoising, but you don't actually know what's causing your data to be noisy, but you've got a few clean examples and you can train something on it. So there are tons of cases where you don't have labels, you don't really know too much about, let's say, the factors that are contributing to noise in your data, and so the only signal that you have to learn on is the data itself. And so one of the examples that we can go into, and I can send you guys the paper if you're interested, is with like human neuroscience data. It's very noisy and we don't know what's going on. And so there we used autoencoders to basically learn how we can denoise data, but then also we learned how we can fill in data that was completely missing. So imagine in like one of the images, like the bottom left 9, let's say you're just missing like 5 rows in the middle. We would like to be able to have a robust representation such that we can fill in that data. And like we might not have a label. Like if it was the entirety of the bottom 9 missing, it could be an 8. But other characteristics about how it's drawn, which we should see in a representation, would indicate how we should like reconstruct and refill it. Does that make sense?
Also, you built an encoder bit because you project your original image on the latent space, and then something is ready.
Yeah, and so that's a good point as well, and that kind of goes back to here. So what you can use and what some people do is they'll train an entire autoencoder. So they'll train from the input data through the representation, through the reconstruction, and then once they've trained it and used this as a way to train, they'll literally throw away the decoder and they'll throw away the reconstruction. So you don't necessarily need it. You can just go like where the arrow tells you and use that representation for a downstream task. So if your goal with an autoencoder is to do reconstruction, you can do it. If you want to do it with denoising, you can do it. If you want to train it in this way and then throw away the back half and just use the representation it gives you, you can do that too. So it's a pretty flexible framework to accommodate many different downstream tasks. Yeah. Okay, make sense? All right. So this next slide is a lot to process and we're going to walk through it, but I'm going to put it up. And this is what Mnist looks like in a 2-dimensional space. And so this was trained with a variational autoencoder. We're not going to go into what a variational autoencoder is. For now, just assume that it's an autoencoder. But I'm just going to put it up, and I want you guys to look at it for a minute and try to see what you can interpret, and then we're going to walk through it step by step, because it is a lot. Okay, so this is an Mnist example. And this is so on the right side, that's the 2-dimensional latent space. And on this left side, it's what the images we create look like. And so what we're going to do now, let me walk through what each side is more concretely. And then I do have a few questions, and I'm going to ask you guys to kind of analyze this plot and see if you can understand what's going on. So on this side, these are sample images generated by picking points in the 2D latent space on a grid and then decoding. And so that was a lot, and let's see if I can tease that apart. So on the far right side, this latent representation of the validation set, what we've basically said is we have this autoencoder, and the yellow piece, which is our representation, we've said it's going to be two-dimensional. You only have an X and a Y. And so what we've done in this lower dimensional space is let's say all of the zeros go to around like the coordinates 1, 2, like literally just the coordinates 1, 2. Well, we've gone and we've picked some random point in the lower dimensional space, and then we've asked our model to basically decode something that didn't necessarily have an image into it at the beginning. So what we're getting our model to do is we're coming into this latent space, we're saying, all right, between the 1s and the 7s, like in that space between the orange and the purples, I'm just gonna pick a point, and I wanna see what that point decodes. So in the representation space, I pick a point, and then I have the decoder do its thing, a already trained decoder do its thing. And these plots are aligned with one another, so when you kind of see where like the space between the 1s and 7s, it would generate a point that looks kind of like that. And so this is probably the cleanest example that exists to demonstrate how you can visualize a latent space for images that you've input, and then what it looks like when you actually do that reconstruction back out. Do you guys have questions? Are you confused about what's going on? Because there are questions coming up, so if you're confused, ask now.
I'm confused. Can you explain how do you extract the left image?
Yes. Okay. So let me. Okay. So you understand the autoencoder piece of how there's this lower dimensional representation, and then we decode and we do a reconstruction. Okay. So the orange blob are basically the ones, and you can see that that's where the ones like get reconstructed to. And then here, this purple area corresponds to the sevens, and you can see that this is where the sevens get reconstructed to. So, and this is tying into something Brady asked. So let's say like this point here. I pick this point in the representation space. So it's, I don't know, -3, 0, something like that. And what I can do is I can give this to my decoder. And then what I can say is, okay, decoder, I give you a point that's like -3, 0. What does that look like if I reconstruct the image? And I would come over here and it looks like something over there. And so to solidify Brady's question, each point in this space is one image. And the idea is that, let me go back a few slides. So the colorful rainbow plot on the other slide that's in 2 dimensions, that's this representation. And then the plot over here with all the numbers in a spiral, that is what the reconstruction looks like if I pick a point and then I get the decoder to reconstruct it. Okay, does that make sense, both Brady and Mingyu? You were going to say something, George.
So one thing to keep in mind is that like the scales don't matter. There's infinite representation until you max out your float. There's an unlimited amount of space in your representation. What matters is like the distribution of the points, right? Because if you correct scale outright.
So everything George said is true. Another thing that I want to add on to it is the goal here, and we're going to get into what we're viewing, but when we're looking at this, you can kind of see that we're not just trying to embed, or at least the model is not just embedding numbers. And you're right, Brady, if like we wanted to have a representation that just gave us very clean numbers, then that's what we would probably want the model to give us. But there's characteristic to the numbers, like how straight is it? How curly is it? How tilted was it written? That are shared across many numbers. And so that's why, like, I think when you look at, I think a good patch is, and I'll do this for Mingyu and them too, like when you look over here at like the 0s and the 6s, there's considerable overlap between like a bad 0, or rather a good 0 and a bad 6. Like they both have the same characteristics. And so when you're actually looking to what the model learns, it's not just learning like the identity of the number, but it's also looking at the characteristics that went into drawing it. And so that would be another, on top of what George had mentioned, why, you know, there isn't clusters that are as cleanly visible. Does that make sense? Okay. Sam, you had a question.
What are the colors in the right
Yes,
plot?
so okay, so the colors on this right plot are the label of the number. So the purple ones are 7s, the orange ones are 1s, and then so on and so forth. So you can kind of see like, and the colors on this plot do correspond to this plot over here. So like 0s are the reds, and you see that like, the 0s are here. So you can make a correspondence between what you're seeing in the left and the right. Yeah.
Is that determined like beforehand? Is that like the ground truth?
Sorry, this?
The colors.
Yeah, so the colors, so we're not, and this goes to, I think it was Nayon's question about whether or not we're using the labels. Here, we're not using the labels in our learning process. So let me go back. So this is what we're actually learning. We're just taking the input data. We're not using the labels of like 0 through 9 in this learning process. We are only using the labels once we have a representation to color the space. So like on day 1 when you guys did PCA, actually let me go back. On day 1 here. On day 1 when you did PCA, in the bottom image, you guys had the downstream task of like, oh, was the intruder female or male, or was the sex female or male? And you didn't learn whether or not it was female or male. You just colored it based on labels you already had. And we're doing the exact same thing in this plot here. We're not using the labels at all. We're just coloring the latent space to see if we get separability. Does that make sense, Sam?
Yeah.
Okay, as well as others. Okay, good. So I will run through these slides. So on the left, just one more time, and if you have questions, stop me. These are the sample images generated by picking a point in the latent space and then pushing it through the decoder, so from the yellow piece onwards, and seeing what we get. That is the process that's going on here. And then on the right side, we're looking at the embeddings of all the images in the validation set. And so we're going to get into in a little bit what the validation set is versus what the training set is. But I think that everyone is now clear on the idea that the right side is the embedding space. The colors are not being used for learning. It's just to color what our representations look like. We can go into the representation space, pick a point, and then decode and see what we actually generate. Okay, for those in the room as well as on Zoom, does this make sense? Yes? Okay, good. All right, moving forward. So these are the takeaways. And we kind of went into this a little bit. For the first one, there's really not meaning to the latent space. Like, for instance, in the autoencoder, when we were coloring by like male or female, there was some clarity behind like, okay, this axis is probably, you can make it very linearly separable to see where is female, where is male. We don't have as clear or as strict guidelines here for what the axes correspond to. And however, we can get a qualitative sense of what happens as we traverse the axes. So to Brady's question, I answered this a little bit before, but I want to ask you guys, what features do you see in this space? And it may be helpful to look at this guy as well when you answer this question. Yeah.
And the one has less pixels, right? Like just one.
Yeah, that's a good one. Do you guys see that? Let me do it on. So Mengyu and Sam, did you guys hear that? So what Amit said was, I can't see my cursor. Okay, so he said there was a pixel feature where on this area, you're not seeing, as many pixels that are white as compared to over here, you are seeing brighter digits that have presumably like more pixels in the actual image, more bright pixels in the image. All right, what else?
The shapes of the way the digits are written from the upper right circular to the lower left.
Yeah.
The zeroist of zeros, and
Yeah.
sevens which share a common feature with ones which are above.
Mhm.
And then sixes may be similar to zeros but are not zeros, may be treated as zeros.
Yeah.
Which also kind of shows us the latent space representation.
Mm-hmm.
I mean, pink, I kind of interpret pink being zero.
Pink, sorry, this one.
Yeah.
Yeah.
Red, whatever.
Yeah.
And let's say orange would be one,
Mm-hmm.
and it gets a bit overlapping with purple, which would be seven. I don't know.
Right. Yeah, no, that's definitely true. So to Mihai's point, so up here, there's like more circular features, and you can kind of see the zeros blending into the sixes, and then even into kind of like the threes and the eights. And then as we kind of come down to this side, there's sharper, so like there's lines versus edges versus curves. Yeah. Do you guys see this? Get this takeaway? Okay. All right, the next takeaway is that this model has no prior concept of what a digit is. And this goes to Brady's point that he made before of like, oh, don't you want it to be like, 10 different clusters? But it does learn to embed each digit. So you've got, a cluster for your sevens, a cluster for your ones, a cluster for your zeros. And it localizes two digits that are similar. So you do see these clusters. But the representation is also useful because it's not just separating out the features. It's also capturing things that we might not have had an easy time like putting into like if and else statements, like the slant, which you can see like as we go along here, like you see the slant of the sevens changing, or the circles as we discussed before, or like as Amit had pointed out, like the lack of pixels up here. So when you ask like your model to learn a representation for you, you don't necessarily know what it's going to pick up on or why it's going to pick up on those things. And that's, I'm sure you guys have heard like, oh, machine learning is a black box. Like there are ways to get at this interpretability, but you're not necessarily always going to get like clean separability in the way that you would expect with like digit embedding. Okay, does this make sense? All right. Okay, let's see. Okay, so let's go back to the concept of an autoencoder where we've got our input data, the encoder is a neural network, there's representation, decoder is a neural network, and then you've got your reconstruction. So what we're going to look at today is what happens when you take the same neural data that we looked at with the mice. So you've got your 115 neurons. We're actually going to shorten the amount of time to make it very easy for you to train. So we're only doing 1,000 time steps. But this will be our input data, and this is actually what it looks like. So this is what you should expect. We're going to embed it into use a neural network to embed it into a representation space. And then we are going to build a decoder. And the decoder will create a reconstruction, and that is actually the reconstruction that it will look like. So you should have a very clean understanding of wanting, and really the way that I want to visualize this is what our autoencoder is doing, as opposed to what our like PCA analysis was doing, where we were taking in like the original data, we were just embedding it into a PC space, and then we were doing some downstream task with it. Here, not only do you get a representation that you can do a downstream task with, and I encourage you guys to like try that if you end up getting through finishing building your neural network, but you also get this interesting reconstruction that you can do things with as well. And one of the things that we alluded to, but we didn't, really explore in depth, is the idea that these autoencoders, should you adapt them a little bit from what we're doing today, you can actually make them generative. So let's say you want to train a model. Let's say you want to train a model to do some classification, but it's with a very rare behavior, and you don't have enough to train any model that is like sizable enough to do it. If you train a model like this, you can actually understand the underlying distribution of your data and generate data points that never existed before. So you are generating examples that you never saw. And so to be explicit, like let's say I really want, like I'm training a classifier, the case of getting a picture that's between 1 and 7 is super, super rare. I can literally pick this spot right here that has no pre-existing data point and like do a reconstruction of that point and see what I get. So it's a very powerful technique that, like the concept of autoencoders, this is a little more sophisticated, but it's a very powerful technique that can allow you to not only, do better embeddings and learn better embeddings, but also generate new data if you want it and you need it for, neural decoding or something like that. Okay. All right. Okay, so this is the autoencoder, and this is what we're going to do today. I want to dive into a little bit about what is kind of underneath the hood of this autoencoder this autoencoder and specifically the encoder and the decoder. So they are both neural networks, and what really does that mean though? So both of these are, we're only going to be doing very simple linear layers. We're not, I know this morning I talked about the convolutional neural networks or the recurrent neural networks. We're not going to do that. We're going to keep it very simple, and we're just going to look at linear layers. And the idea behind what a linear layer is you have these dots, which are artificial neurons, and you can connect them to another layer of artificial neurons. And if you just had, we're going to go into this actually a little bit more. So this is your linear layer. And let's say that you just had these artificial neurons and they connected to another set of artificial neurons, and you didn't have any nonlinearity, you just had that. Then a linear layer is really just a matrix that multiplies the input and produces some output. So it can be smaller dimension in the case of the encoder. In the decoder, it can be a bigger dimension. Really, a linear layer is just a multiplication. Okay. However, if you just compose 2 linear layers, you're just going to get something that's linear. If you don't introduce a nonlinearity, you will not get something that is a more complicated representation of your data. And so what we need to do is increase the expressiveness of our model by adding these nonlinearities. And today we'll go into this a little bit more. We're only going to deal with ReLU, which is a type of nonlinearity. But when you're going through your code and you're actually like typing it in, understand that adding that is the magic sauce that allows your network to actually learn something that is more than just a linear embedding. And I'll leave this as an exercise to the reader, but when we go back to like our encoder or our autoencoder and specifically our encoder, this looks very similar to PCA. And if you just keep your encoder as like a linear matrix operation, you can make this exactly PCA. The only difference between this and PCA is that we flipped a network and we added it, and we're adding nonlinearities. So really think of it as the same. So it's very conceptually similar. Okay. All right, we did that. So now let's talk about nonlinearities, which is the thing that allows us to learn these more complicated representations. Okay, so functionally, nonlinearities go between our linear layers, so they're not really visualized in most of like the neural network architectures that you're going to see. You're just going to see something like, where's my cursor? Something like what's on the right of the screen with the images. And so our nonlinearities will go between these, and they're called activation functions typically. And when you compose all of these layers together, you're going to get some complicated nonlinear function. And this is what allows us to build universal function approximators. And so when you've probably heard like, oh, deep learning, it's a universal function approximator, the only reason is because you're taking simple nonlinearities and you're basically doing multiple layers of them. So like, we can go into this a little bit if we have time, but if you're looking at like a convolutional neural network, the different layers and the different filters that you learn, you might get like edge detectors or, you know, like curve detectors and different things like that. And sometimes in deeper layers, you'll literally get like face detectors and dog detectors. It's kind of creepy to look at. But the only thing that's allowing that is just literally the composition of many, many nonlinearities on top of one another. And these nonlinearities are very, very simple. And we're going to look at how simple they are in the next slide. Okay, so I mentioned this briefly on the last slide. Nonlinearities called activation functions, same thing. There are many of them, and there are many more than what I'm going to put on the slide. I just want you guys to see them so that you're aware there are many options. So the first one is called a sigmoid function. We're really not going to go into the math. I just want you guys to see it and to get like a visual of the different options to make our model nonlinear. Another is called tan-H, and so it's a very similar shape, but it's just shifted down the axis. We also have a leaky ReLU activation function, and then we have the ReLU activation function. And so today with the notebook that we're going to be building, we are going to be looking at ReLU, and we're just going to be using ReLU. So there are pros and cons with using each. Pretty much everyone in the machine learning community just uses ReLU. It's not something that people tweak with too much. If you would like to experiment with using another one, you are welcome to. So to recap, these functions basically go between the layers of the neural network, and that is what makes, when we do our matrix multiplication, that's what adds this nonlinearity. It's a very simple function that gets added, and that's the only thing that we're doing. That's what makes it nonlinear. Okay. All right, let me pause here and see if there are any questions, because what we're going to do is we're going to jump ahead a little bit to teach you guys about what training looks like, because we're going to skip a little bit, because if you guys want to be functional on it, we can't go into everything in detail. So if there are any questions, ask them now before we jump onto another topic of how you actually train these neural networks.
Just one question. How many layers do we need to train?
How many layers do you need to train? It depends on the task.
How do I know, like, which task?
How do you know, like, when you've done it enough?
Yeah.
Or when you, okay. So we're going to do that with the training slides. We're actually going to walk through examples to know whether or not you are learning or not learning or doing too much. Yeah, so we're going to do that in a few slides. Okay. Any other questions? No? Okay. All right. So we're going to jump ahead to training. And so the first question that I have, yes. Okay, so specifically underfitting, overfitting, and how to read training validation curves. Okay, so the first question that I have, and I want somebody in the audience to answer, is what is the training set versus the validation set? Who knows? UA, do you know?
Training set and validation set are both from the data set you collect. Training set is used to build your model, and then it's used to change the parameters in your model. And when you're using your model on the validation set, you will set all the parameters fit, like settle down, not changing, and then use your validation set to see how well your model performs on the task that you want your model to perform.
Yes. Okay, did everyone hear that? All right. I will go over what you said one more time. She did a very good job of explaining it. So essentially, you have lots of data, but when you train a model, part of what it's doing is learning what's in the data. And so let's say I have 100 examples. I don't want to train my model on all of those 100 examples, because what if I just memorize those examples? And this happens with deep learning a lot. It's a very powerful function approximator. So it literally can memorize all of the noise that you're putting in, all the little jiggles, it can memorize it all. And so what we do is, let's say we want to do a 90%, 10% split. If we have 100 examples, we'll use 90 of them to train with, we'll hold out 10 of them, and we're not going to let the model learn from them. So we're not going to update these weights from them, we're just going to keep them separate. What we do is we use those 90, we use a neural network, we go through those 90, and we update our model parameters. So in the morning lecture, there were those thetas, and those were the weights you were learning for your network. We learn those thetas with the 90 that we have. But we don't want to overlearn to those 90. We don't want to fit too much to those 90, and that's called overfitting. So what we do is we say, okay, every once in a while, perhaps at the end of every epoch or at the end of every 5 epochs, epoch is just one loop over all the training data. What I'm going to do is I'm going to stop training my model. I'm going to put it in an evaluation mode, and I'm going to see how it performs on this validation set. And when I see how it performs, I can look at the loss curves between the training data and the validation data, and depending on what they look like, I can know, am I overfitting, meaning I've memorized the training data? Am I underfitting, meaning I haven't learned enough? Or am I right in the sweet spot? Okay, does that make sense? Okay. Yes? All right. Okay, so, okay, that's not supposed to be there. That's,
Is it all
yeah.
separate when you train the model, or do you do the cross-validation?
Let me so what we are going to do today, I don't know why this is showing up. What we are going to do today is, sorry, one second. Okay, so this idea of doing cross-validation, that is basically when I don't have enough data. So I don't have enough data to actually learn it. So what I'll do is I'm going to take all of my training data, and I'm going to, let's say, 100 data points, I'll split it into groups of 20. I'm going to hold out 20, I'm going to train on 80, and then I'll test it on that 20. But because I don't have enough data, what I'll then do is I'll pick a different 20, and I'll train on the other 80. And so that's basically a way to get around the fact that you don't have enough data. And so in the ideal case, you have enough data points such that you have a separate train set, a separate test set, and a separate validation set. And so ideally, today we're only going to have a train set and a validation set. But ideally what you have is people do an 80-10-10 split. So 80%, 10%, 10%. So I have train data that I train on, 80% of it. I have validation that I check to see how I'm doing, and that's about 10%. And then there's a test set that I literally do not touch. I do not see it until the very, very end. And if you guys want to learn more about this, you should take Esong's machine learning class. I think it's CS 155. But what they do is they actually have a Kaggle dataset challenge. And Kaggle is basically it's an online thing. So you could actually go do a Kaggle challenge right now if you wanted to. But what they end up doing is they will give you a train set and they will give you a validation set. They will not even give you the test set. And what you do is you will submit your like parameter values to this like website, and then they'll tell you like what your scores are. And so the idea is, and if you take Yasser, who's another Caltech professor, his I think it's CS 156, he describes the same process where he literally like kept the training or the testing data from everyone and only like made them submit their models or submit like their parameters to him. So in the ideal world, you do not touch your test set until you are sure you are done. You only work with the train and the validation. But of course, you have to have enough data to do that. Yeah. Yeah. Another important thing I want to mention before we keep going is, and you guys are going to deal with this a lot because you have animals and the animals change across different days. Or so like, let's say you're recording in one animal and then you look at it day 2, day 3, day 4, there's going to be some distribution changes of like the neural data you're recording. In addition, let's say you're looking at population data from many, many animals. They're going to be different because of, I don't know, how hungry they are, how thirsty they are, et cetera. One of the really important concepts that we're glossing over is the idea that the training data, validation data, and testing data all comes from the same underlying data distribution. And you're going to see this a little bit in the notebook today as well. But if, for whatever reason, the distribution changes, let's say you're collecting data over, I don't know, a month, and then you train it on like the first 2 weeks, and then you test it on the next 2 weeks. There's nothing to guarantee that that data comes from the same distribution because your electrode shifts or whatever. And so make sure that when you train something, you do the best you can to say that, and to say and see that the data comes from the same distribution. So another important thing to keep in mind. And we will see it a little bit in the notebook, but not too much and not necessarily by name. Okay, so underfitting. Underfitting is when the model doesn't have a low loss on the training set. And what that means is that the model hasn't really learned yet. It can keep learning. And I don't know why these slides are showing up. Let me delete this. At least it's not the answer. Okay, and then overfitting is when the model starts to basically memorize the training set. Okay, so now what we're going to do is I'm going to show you the plot of a validation curve, and I'm going to show you the plot of the training curve on top of one another, and there's 3 different instances. And I want you guys to basically brainstorm and then tell me, what are we seeing? Are we seeing underfitting or are we seeing overfitting? Okay, they're showing up at the same time. Okay, so let's go to the next slide. Okay, but it shows up. Do you guys get this? Do you guys get like imaginary view? Okay, imaginary images. All right, so this is the first example. So the blue is our training set, the orange is our validation set, and are we overfitting or are we underfitting? Or maybe neither. Why don't you guys discuss amongst yourselves, and then I'll have you raise your hands to what you think it is. Yeah, and Mingyu and Sam, you guys are free to discuss as well and contribute. Sorry? The x-axis is time, yeah. Sorry, I should have included that. Yeah.
I think you're right. That makes sense. Because otherwise, like, right. They should be close to it. Although, to be fair, the absolute value is pretty small. Right. Yeah, I guess it's like hard to say because like if you compare it from here, right? These are like close to the other things.
No. So together they are underfitting. You have to always consider the train and the validation at the same time. Oh.
Yes.
Yeah, that's different. Sorry. Yes, those slides. Look at this one. Don't look at that one. That's pictures just showing up. Yeah, if you guys are looking at the slides online, there's like an invisible figure that keeps showing up so look at this one. Don't focus on the one that you guys have there. Okay. All right. It seems like people have somewhat reached consensus, or at least we're quiet now. Okay, so who thinks that this is underfitting? Raise your hand. Okay. Who thinks that this is, wait, raise them higher. Okay, what's this? Raise them higher. Who thinks that this is underfitting? Okay, I can't even tell. Is this like 50%? Who thinks that this is overfitting? Okay, so we're like 50-50, I want to say. All right, this will be fun. Okay, so this is underfitting. And the reason is because flat loss curves indicate that the model isn't learning. So if your loss is not going down, your model is not picking up anything. So you are not learning anything, nothing is happening. All right, does this make sense?
I thought my reasoning was that this is a loss function, right? So the lower it is, then the better fit, right?
So I wouldn't, okay. The thing with loss functions is lower is better, but it's all relative to what the loss function is. So maybe this is actually very high for the loss function, or maybe it's very low. I would not focus on the absolute magnitude. I would only focus on like the relationship between validation and loss, and like what is the slope? What does the slope look like of both of the curves? Does that make sense?
Right, but there is still a difference between validation and train, right?
Yeah, you mean in like their slopes?
Yeah.
Yeah, so there's a difference, but they're still both going like kind of down, but pretty flat. Yeah, okay. All right. Okay, we're gonna move on to the next one. Okay, this is the next one. So discuss amongst yourselves, is this underfitting or overfitting or neither? Maybe it's neither.
Going down, but it's not, it hasn't like leveled out again. And then kind of like what you're saying is that they're still varying. So, and the fact that validation is going to train to make something. Yeah, but you can expect them to convey the same case. But there's always going to be a little bit of a gap. I think it's weird that the validation is.
Yeah. Sorry, say again?
Should they converge?
Yeah, so I mean, ideally, when you've learned something, your loss is going to level out, right? Level out. It'll plateau. Once you've learned something, you will plateau. Okay.
Or I don't think it's like. I don't think it's not. I think it's just. I mean, it's weird. Can either be? Is it like? Is there a dichotomy between underfitting and overfitting? I feel like.
Is there a what?
Is it a binary?
Yeah, I mean, you've either, so like you either haven't learned, or you're kind of just right, or you've like memorized. So I mean, obviously it's like, there's not like one epoch where it shifts. There's like a little bit of a range, but yeah. You can't both not know the data well enough and be memorized to the data. Yeah.
It seems like we're past like the highest derivative point, but especially if you like we're at the same time. And there's no guarantee. It hasn't like leveled out. Like I think it's learn more.
Yeah, but you learn more both from underfitting and
Yeah,
All right. Okay.
but it has already started now. I don't think it's done.
Okay. It seems like we're a little quieter now. Who thinks that this is underfitting? Okay, raise your hands high. Come on. Underfitting. Overfitting. Okay, not everyone is raising their hands, so it's very hard to tell if this is 50-50 or not, but there's people on both camps. Okay, so this is underfitting because we haven't yet converged. So you can see that both the training and the validation losses, they're both going down. And so if they're both going down, we haven't yet learned everything that we can yet. Okay, does this make sense? Yes, yeah, okay, so sorry, just explain it. Okay, so underfitting is the concept of like when a model doesn't have like a low loss on the training set, which means that it hasn't learned. So this model is learning because the loss is going down, but it hasn't yet plateaued. And because it hasn't yet plateaued, we can still learn more. And because we can still learn more, it's underfit to the data. So we can do better. Does that make sense? Laura?
I have a question about the first graph.
Yeah.
If the slopes were going down, but there was this gap between validation and training, so the loss for training would be very low, but the loss for validation would be high. Would we, in that case, call it overfitting?
So really, the thing that people look to is when does your validation loss start going up and when does your train loss keep going down? And so basically when validation starts going up, but train loss starts going down, what that tells you is that we're at a point where I'm starting to memorize because my performance on like the holdout set is like getting worse. And that just means I'm memorizing the noise, I'm memorizing like all the little errors. So really it's that. If, so like here you can see that the train and validation plots, like they're flipped. Like on this one, validation is on top, and on the other one, validation is on the bottom. But they're both underfitting because you're not quite learning the train set yet. Like they're on the first one, it's relatively flat. On the other one, they're going down. Don't worry too much about that. Worry about when does validation go up, but train keep going down. Okay. Does that make sense to everyone? Do you have a question?
What are the cases when training loss is always higher than validation loss?
Yeah, I mean, so it really goes back to the thing I alluded to before, which is the data set distribution. So you're gonna randomly select, like oftentimes, you'll have PyTorch do it for you. You're gonna randomly select points that belong to like the validation set or to like the train set and the test set. And so sometimes like you have a very clean underlying distribution and maybe you just get lucky and like your validation set is more representative of it. And so, or maybe sometimes your training set is more representative of it. So it really depends like how well does your data set look like the underlying distribution that it's trying to learn. And if the validation set is a lot cleaner of like the underlying distribution, then like you might get a better validation loss. Does that make sense?
So if you just continue to the validation goes up and the training goes down, if we're overfitting, we want it just to contact.
Yeah. So ideally what we want is we want it to plateau, and what people will often set as like a criteria to stop training is they'll set some like threshold. So like if my training loss and my validation loss, if they haven't changed for like, I don't know, I'm just gonna random units. If they haven't changed within 10 units over like 100 epochs, I'm done. There's like more research on this. There's like new phenomena where if you just keep training even after plateau, it'll suddenly like start to generalize. But for now, yes.
Actually, what I want to ask, can it start overfitting after it's deploying?
Yeah. Because the idea is that when you've plateaued, like you're learning. So basically underfitting it's kind of like Goldilocks, if you're familiar with that, if you guys are. So like Goldilocks, it's like, is the porridge too cold? Is the porridge too hot? Is the porridge just right? And so the way I look at it is you're underfitting, which means you haven't learned enough. You get to the space where you're learning just the right amount, like you're not over learning to learn the error. But then if you keep going, you're just gonna like start memorizing. So think of it as like, I haven't learned enough, I've learned just the right amount, and then like I'm starting to memorize. And so that's the point that you're trying to tease out by plotting the validation loss as well. Like what is that happy medium? Does that make sense? Okay. Any other questions on this? No? Okay. Last example, what is this one? Well, you can discuss if you want. could be wrong.
Could be. But at least we are all together.
That's true. That's good partnership. All right, everyone seems pretty quiet, or at least less talkative than the last time. So is this underfitting or overfitting or neither? Who thinks that it's underfitting? Okay, who thinks that it's overfitting? Okay, pretty much everyone. Okay, good job, you guys. It is overfitting, and the reason is because the validation loss is going up while the training loss is going down. So like the orange, you can see, I would say it's probably, I don't know, around like, 75 to 100 epochs. That would probably be like the right time to stop. But then after that, you're starting to memorize that training, and because you're memorizing, you get a worse performance on that holdout set.
So what confused me is, like, as you mentioned in the first day, that you have like this local minimum, right? And that's like kind of overfitting that you can get. But here it seems like you, after the local minima, you get to the local maxima, and then you can continue and find another local minima somehow.
So you're saying with respect to the training data set?
Yeah.
Yeah, so the loss, it's very hard to think about. So you should be thinking about like local minima versus global minima in this context of like deep learning, but the loss landscapes are much more complicated. So it's like, there is no closed form solution to know like what is right. Versus on the first day with what you guys are doing with like logistic regression and linear regression, there is a closed form solution. Like if you want to figure out exactly the right spot, it exists. We do not have that intuition here. And so really, so like for instance, on the one where we're overfitting, like you're right, maybe if we kept training, and what people will do is sometimes they'll add like some just like bounce to the data. So like they'll kick the gradient to like some other location and see if it goes somewhere lower. And so people will do that. But we don't know where we are. We don't know if we're close to a global minima. We don't know if we're in a local minima. We don't really know. So what people often do is they'll just initialize the training to be in like different locations. And so they'll start the parameters somewhere else and they'll see where it converges to. And we're only gonna run, I mean, you guys will have the opportunity if you want to, but we're only gonna run one seed. So you have to set like a PyTorch seed, you have to set like a NumPy seed. We're only gonna set one seed today, but you can use that seed to basically start your parameters in a different spot. And that will allow you, if you like average across 5 seeds, you get like a good understanding. Yeah, but you don't obviously know. Laura.
Can you view the x-axis of these graphs as like epochs?
Yes.
And is each epoch like a step in a gradient of these?
So one epoch is one entire loop over the entirety of your data set. And so depending on it, so it depends on whether or not, like when you're updating your gradients. So sometimes people do it after each batch. Sometimes your batch is your whole data set. So it really depends on the specifics of like the code that you're working with. Yeah. But yes, think of the x-axis as like, you can think it's basically like the number of epochs, but you can also think of it as like time spent training. So the y-axis is like the amount of loss you have, and in all of these cases, lower is better. Sometimes you can do like maximization instead of minimization, but x-axis is just time and or like number of epochs. Yeah. Okay, does that make sense to everyone? Good. Okay, now I want you guys to talk amongst yourselves about what you think a well-trained model will look like with respect to the training and validation losses. You can even draw it on your tables if you want.
Yeah. It'll look like that, but like before.
Are you already done? You're experts.
Yeah.
Like one line would be almost but this one would just
Okay. All right, it seems like people have figured it out. So does somebody want to shout out what they think it's going to look like?
We should follow the same inverse exponential shape.
Okay, so both the train and validation are going to follow the same shape, and you're saying that they're going to plateau as they come across. Okay.
Yeah, it's exactly what I want to say.
Okay. You said it very eloquently. All right. All right, so let's come back. Let's look at what it actually looks like, and then if we want to keep discussing, we absolutely can. So what it's going to look like, as many of you discovered, is the train and validation loss. They're going to kind of come together, and they're going to plateau out. So that is what indicates that we're doing it correctly. Okay, so everything you learned, and I will fix the version of the slides to not have those little mystery images. This is all going to be very important for the notebook you are about to do. You are going to have to use everything that you just learned to figure out whether or not you are training it properly. And I know that we went over a little bit today, but try to get through as much of the notebook as possible and ask for help, because next week we're going to dive into deep learning. And so going through this notebook is going to be very, very beneficial for you getting everything you can out of next week. Okay, all right, thank you all. Let's start coding. Mengyu and Sam, do you guys have any questions?
Yeah, I have a question. So in this case, they're both I guess plateauing. In the previous example where you showed overfitting,
Yeah.
Are you looking at essentially the orange curve is rising ever so slightly, or it's not decreasing, or
Right. So what we're looking at here is that it's both that the orange curve is rising so the orange curve, which is the validation curve, is rising while the train curve is going down. And what that indicates to us is that the validation curve, which is the held out data, is no longer, we're not getting a good loss, meaning we're not doing good prediction. And because the training set keeps going down in the loss, it means that our model is basically memorizing that training set. And so because the model is memorizing the training set, it starts to perform worse on the held out validation set. And you know that around then is the point where you want to pull the plug on training, because you've learned everything you can, at least with this architecture and this loss function.
I see. But is this just a matter of when you stop the training? So it's up
Yeah.
to I think you might have said this, but up to maybe 75 or maybe 50 is appropriate, and then after that it's overfitting.
Yeah. So I mean, so what I would do in reality is I would basically find out what is the lowest value of the validation loss curve. So it's around, I don't know, 75 to 100, something in there. I would literally go and just find where that is. And on the epoch where we have the lowest validation loss, that is the model that I would save. And that would be the best performing model.
I see. Okay, gotcha.
Yeah.